Everybody. Hello, ladies. Others might join us as we jump in. I got a couple emails from everybody. You guys are so polite about responding to my request for online class. What was I going to say? So real informal. I just got a couple little side notes that I'm going to use here and discuss what I got from you guys in terms of survey results and emails, although some of the emails came in like literally this morning, so I didn't really have time to process them. But so I want to try and do everything for you guys. So first and foremost, before I even get started with survey results, I'm going to share my screen with you guys. And I want to show you now on my website, and this I think was in the email I sent out to you guys, under student alumni. I've got a couple really good emails now back, videos from former students at the bottom of this page. And I've even put some links here to jump to the bottom of the page here with some great advice for you guys moving forward beyond high school. So both of these young guys are still finishing their computer science education. So they're post-secondary students like you're about to be. But I also have set up some interviews for next week with some other students, former students, alumni, who are now in the industry, some as long as 15 years working in the industry, who I taught back in the day. So I hope to get some great videos for you guys up for those ones as well. So I want to make sure you guys had that available so you knew about it. Yeah, okay. So what I wanted to say was the results of the survey that I gave you guys, because if you might remember, I gave you guys a survey as to what you'd be interested in studying. And what the result of that was, let me put myself on camera here. And I'm just reading off the sheet where I wrote it down, was the number one thing that people asked for from the IB was control, and then networks, and then computer organization. So that's a little bit of essentially computer hardware. But what the non-IB stuff that you guys asked for was algorithm analysis. That was number one. And then it was kind of a tie in number two between graph theory and hash tables. That's purely from the survey. From the emails, there was about 3 or 4 things that people wanted me to discuss. Hash tables was one of them. Design patterns was one of them, which is interesting. And then just some, again, I think it was throughout many of the emails was to help get ready for the next level. So depending on which program each of you is going into next year, you wanted a little snippet of that. So actually, that's the next thing I want to show today. Today, I wanted to focus on the next level at the University of Manitoba. What I think I'd like to do next week is focus on the next level at Red River College. But it's all good stuff for everybody because there's a lot of overlapping content in all these courses. Even if the course name doesn't quite have it matched up, the content for sure would, I think, connect together. So here are the 1,000 level courses at the U of M. In other words, first year courses, and we've seen these before. Some of these are specifically for engineering students. Some of these are just general computer courses that aren't really computer science courses. Both of these can be taken with your IB credit, but this second one, I happen to open up the course outline for it, and you've seen this before. The one thing on this course outline that we definitely didn't cover in our IB course was also something that you guys put into the survey. Algorithm analysis, studying algorithms, best case, worst case, etc. Okay? I'd also then like to go back and take a look at the 2,000 level courses. And the very first course you take at a second year computer science is analysis of algorithms. So I've actually opened that one up as well. And in this course outline, I'm going to point out a few topics here. One, obviously, dynamic programming, divide and conquer algorithms, linear recurrences, which is part of recurrences, greedy algorithms, okay, and this I can't say it, notation is, again, this big O notation. It's a weird way, by the way, that this professor wrote that, but would be essentially the same thing that you would have seen here. That's what that O represents right there. So that's kind of what I wanted to discuss today. I'm recording this, and you guys can drop in and drop out or ask any questions you guys would like. But I'm going to teach this lesson essentially the same way I would teach it in class. And to do that, I just realized I wasn't sharing my screen, and now I'm going to share it. I'm going to go back and re-show you that again, that those courses at the U of M, I'm right here, Department of Computer Science, the 100 level course, Intro to Computer Science 2, and the 2000 level course, Analysis of Algorithms. Okay, and here are those course outlines. So here's the Introductory Computer Science 2, the first year course, and this is at the end of that course, that Introduction to Analysis of Algorithms, including something called Big O notation. This is the course outline for the second year course, Analysis of Algorithms. And if we look at its course outline, you can once again see that Big O notation, as well as greedy algorithms, linear recurrences, divide and conquer algorithms, and dynamic programming. So I'm hoping today to talk about essentially all that stuff. So what I want to talk about today, and I tried to install the notebook software we use in class, and it just wouldn't let me on my laptop. So what I want to talk about today is that idea of, oh, that's not going to work. I want to draw on this, but I also want to add, is algorithm analysis. That's the topic I want for today that we're going to talk about. So I'm going to do it in some ways in a traditional way, like we would in class, and then in a sort of non-traditional way as well. At the end of this, I will put this video up on our website, and I will put some additional links to some additional resources for you guys on how to study this computer science topic of algorithm analysis. What algorithm analysis essentially means is deciding which algorithm is best, and instead of the word algorithm, I'm just going to say which way is best. And there's a lot to sort of unpack in that, even in that sentence, okay? When I say way, what do I mean, right? Like what do I mean in a computer science context? So I could mean the algorithm, okay? Which design is best? Which, say, search is best? Which sort is best? There's lots of different ways I could analyze that sentence, right? Like when I say way, and what do I mean by best? Does best mean like cheapest? If I was running a business, does it mean fastest? If I'm talking about things like video games and processing, does it mean fastest for the computer to run? Does it mean fastest for the programmer to get it done? So if you're in a business and you need to get this done within a couple months, would that be the best way? So best is a word to analyze. Way is a word to analyze. And so when you analyze an algorithm to figure out which is best, that's essentially kind of what we're talking about there. We're talking about which way is the best way, and it's a deeper question. Okay, so let's take this word and even go a little further into what I mean by best. Okay, so when I say the best algorithm, okay, could I mean the fastest for the computer? Okay, so we saw when we did our sorting unit that some sorts are faster than other sorts. They can finish the job quicker from a computational standpoint. But what about memory, right? If a computer requires a ton more memory to do one algorithm and a lot less memory to do another, even though it's slower, maybe that makes it best, okay? What about the programmer time? If one algorithm constantly needs programmers to keep it up to date, whereas another algorithm can be written once and left alone, maybe that means it's the best algorithm. So, and as I've mentioned before, there are other things to sort of consider there. So with that in mind, I'm actually going to start this little presentation here on the efficiency or the best algorithm you can have. Okay? So this is definitely an important thing in computer science in general. Which algorithm you pick, and again, algorithm is a very open-ended word, which solution that you pick is going to have a big impact on you as a programmer, as a boss, as a student. So you want, for example, video games to work really quick. You want databases to be incredibly accurate. You want a life support system in a hospital to be really, really crucially on task for what it's doing. So the time and the efficiency of an algorithm depends on a number of things. So suppose two algorithms both did the same thing. So for example, a search. What does it mean to say one algorithm is better than another? Well, we could include things like how much human time did each algorithm take? So if you were writing two search algorithms and you could get one done in 5 minutes and the other one took you 4 days to write, and if one algorithm you could write it once and it would always work on every case, and a different algorithm would constantly need to be maintained and updated, then those would both have a cost to them. Not a financial cost necessarily, but an actual processing computer human time cost. Okay, what about the execution of the program, the amount of time? This is usually the one most people go to first. They think one algorithm is better than the other because it's faster. And then the third one would be things like the space that a computer's memory needs to run an algorithm. With human costs, things like style of an algorithm, readability, design, those are all things we've been working on as programmers. A well-designed algorithm would have good problem solving, good style. It would follow a good development cycle, okay? But in a lot of what I'm going to talk about today, it's going to sort of avoid that because that is stuff that's just built into you as a programmer and something you develop over time as a programmer. And instead, we're going to go to a more sort of a more pragmatic, a more sort of computer-based solution, which is more efficient in those terms, okay? The speed of the processor, the way an algorithm operates, the time and the amount of computer memory required for an algorithm to execute, okay? This is a big topic. There is a lot to analyze in algorithms themselves, okay? And it's not really tricks that you're doing here, but it is figuring out which one has a more efficient solution than another, and it's dependent on a number of factors. Okay, including mathematical factors. So we're going to do a little bit of math today in our discussion of algorithms. All right, so let's take a simple linear search. Now you might remember, jump back to the drawing here, a linear search, oops, okay, is if we have, let's say, an array, a simple array with some numbers inside. Okay, the linear search, which means in line, if I'm searching, say, for the number 4, that's the number I'm searching for, I would start at the very first element in the array, and I would just keep going through the array until I find it or I don't find it, and that's where I would stop and say, right there, this is where it is. So the linear search requires you to start at the beginning and go through the entire array. Okay, so a linear search is dependent on the length of the array. The array I just showed was only 4 elements, but what if it was 4 million elements? So what I'm going to say is the length of this list or this array is n elements. So when it has n elements, the best case scenario for finding it is I find it on the very first element. I find it right away. So that would need one check for me to find it. That's my best case. The worst case would be I'd go through the entire list. So n elements. So best case 1, worst case n. How is that then fed up in terms of efficiency? Well, on average, it would be half of that, right? So the average case would be n divided by 2 comparisons. So as n gets bigger and bigger and bigger and bigger, it really doesn't matter whether we're talking about n or n over 2. So when we talk about the efficiency of a search or a sort algorithm, we just kind of assume worst case scenario. We kind of assume that we're going to have to go through the whole thing, or order n. So the order of how big this thing will be is n number of things. And this now is the first notation you're going to see with algorithm analysis in computer science. The word order, okay, is used very often, which is why the notation is to just use the capital letter O, or what's called the big O notation. So big means capital. So the big O notation. So in other words, for a linear search, the big O notation is it would be an order of n elements for me to search that list. In this case, an order of 4. So the worst case scenario of me searching this list would be an order of 4. Okay, and again, these are mathematical terms, so don't get too hung up on them. All right, so let's say we had this little algorithm, travels through a linked list, starts at the head. Well, it's not a null. It's going to move to the next item and the next item and the next item, and it's just going to output what the data is each time. So along the side there, you can see the comments. So in the first line, I assign a node to the head. Then I use a loop, comparing it n plus 1 times, depending on how long the list is. I'll do an output. I'll do another assignment, and that's my while loop. Okay? Assuming this list has n number of nodes, it would require n plus 1 assignments, n plus 1 comparisons, and n write operations. And so if we were assigning a time unit to each of those, okay, with its own letters, right? So A time units for assignments, C time units for comparisons. And I know time on a computer scale is very small. But let's say it took 1 second to assign a value to this, right? So 1 second for me to do the very first line right here. 1 second for that. And then the comparison right here, like checking to see if it's null. Let's say that took 2 seconds. Okay, so 1 second for this, 2 seconds for that. Okay, and then when I spit it out onto the screen, or I write it to the screen, let's say that took 3 seconds. So it would be in a list of 10 items, 10 plus 1, 1 plus 2, and 10 times 3 would be a way to add up all the amounts of time units it would take in terms of seconds for me to do that, if I was to analyze it purely mathematically like that. And I could actually figure out exactly how long this algorithm in time would be take to complete. Okay, so it's proportional to n, right? That time in seconds would depend on how big the list itself was. So obviously it makes sense. That's going to take a lot longer to deal with 1,000 items than 10 items. That's pretty easy to figure out. But what if we had a loop what if we had an algorithm that had loops that were nested inside of other loops, like a series of nested for loops? Now the math gets a lot more complicated. Now the math has to deal with sort of things in a different perspective, right? So time units would depend on things like K and T and J, if you look at me using these mathematical letters there. And you would have to put a lot of math time in to calculate the sort of efficiency of that algorithm from a mathematical perspective. So for those of you who love looking at math in this way, you can absolutely use a unit and an analysis in a very highly mathematical format. So you're going to see that. You're going to see some of these summation and mathematical connections to computer science. I remember in my degree, these types of courses did have some heavy math components to them. But once you break it down into kind of what it is something to essentially get through. Okay. So an efficiency is a function of size. Okay, we already said that's really easy. So let's say we had an algorithm called algorithm A. It required n squared divided by 5 time units. So let's say n was 1,000. 1,000 squared divided by 5 was the amount of time it said to solve this problem on n elements. Then we had algorithm B. It needed 5 times n time units, so 5 times 1,000. Okay, so there's 2 algorithms. Which is the better one? Which is the more efficient? What if n was 10? What if n was 5? What if n was 1 billion? Which algorithm would be better? Well, one thing we can often do in mathematics is to compare these 2 essential functions, a function A and a function B, by graphing them. And if I was to graph those 2 algorithms, they would show up like this on a graph. And there would be a point around 25 items where the 2 algorithms would differ. So at first, algorithm B seems to be taking a lot longer, more seconds, whereas algorithm A is a lot faster, takes less seconds. But then after 25 items, algorithm A is getting exponentially slower, whereas algorithm B stays constant over time. Okay, so there is a sort of a point on the graph where B would be the more efficient algorithm, and then prior to that, A would be the more efficient algorithm. So often when you're studying algorithms mathematically, you tend to ignore the small problems, small values, and assume very large values for the number. Okay, that's not always the case. In some cases, that's not true. And that's why there's a lot more to algorithm analysis than just pure math. But let's go with a binary search. The binary search, you might remember the binary search divides a list in half and keeps searching half. Best case is still 1, but the worst case scenario in a binary search is log 2n. And again, I'm not here to teach you guys logarithms, but that is a lot smaller than n. You do not ever need to go through an entire list with a binary search like you would with a linear search. And I'll just remind you of that. So with a binary search, let's draw another array. However, with a binary search, the array has to be sorted. So let's put it in a certain order, 2, 4, 6, 8, 10, 11, and 13. Okay, so in a binary search, if I was, say, searching for the number 4 again, it starts in the middle. And it says, is this the 4? And if it's not, this whole half of the array is ignored. And now I know this isn't the 4, but I know I can only search on this side of the array now. And I do it over again. I take this whole portion of the array and I cut it in half again. And now I say, for example, with the 6, is this the item I'm looking for? No. Okay, well then this side is out. I cut this in half. And let's say again, I go to the 4 here. Is this the 4? Yes. So it would have only taken 1, 2, 3 checks to find the number 4. Whereas if this was a linear search, it would have taken, worst case scenario, n number of searches. Okay? So a binary search is more efficient from a time perspective. Log 2n is way more efficient, especially with huge, huge lists. That's way more efficient. So bubble sort, selection sort, both used a series of loops on a list. So they both will have a time efficiency of n squared, okay? Because you have to repeat a loop inside of a loop, or n times n, okay? So bubble sort and selection sort are said to have an order of efficiency or a big O notation, okay? So the bubble sort would be an order of n squared, okay? So this is the linear search. The linear search would have an order n efficiency. The bubble sort, and again, I don't want to remind you, I don't want to rewrite that algorithm, but you might remember it as a for loop inside of a for loop of an order n squared, okay? The binary search, where it divides it in half, the one we were just looking at here, has an order of log 2n. And logarithms is, again, something that you haven't necessarily studied, but it's a lot faster. And that's the binary search, where I keep dividing it in half. Okay? So there's an efficiency feature there. Now we could maybe lay these out in an order, right? Like which is faster. So this would be the number 1 fastest algorithm, right? It's way faster. This would be the number 2 fastest algorithm. Okay? This would be the number 3 fastest algorithm, or the slowest algorithm would be the bubble sort. So you can start to see a way to rank them in a certain order, okay? So the big O notation, a simple way to think of it, and maybe I'll just key this in. So big O, okay, is like a movie rating system. That's a way I thought of that analogy. Right? So like this is a 5-star movie. So when you look at the order of how fast an algorithm essentially is, binary search has a better rating than bubble sort because it has a better order of system. Okay. So algorithm A is proportional to the function of how many elements, and that's the notation, the order of. It is kind of like a math growth rate function. The letter O denotes this thing called big O notation. So an algorithm of n elements proportional to n is said to have an order of n, or n squared, or log 2n, okay? Expressed mathematically, you can definitely dive into the mathematics behind this. I'm not going to do that, but you definitely could. You can look back at these slides if you'd like and take a look at sort of how those are worked efficiently in a mathematical sense. Let's summarize these. So order 1 would be the fastest possible thing, right? That's the fastest algorithm you could possibly make, right? It's not, I mean, you can't do much with that. That's like me saying int x equals 5. That's an order of 1. It's done right at that point, okay? Log 2n, logarithmic time, very fast, okay? Linear time, order n, okay, is as long as there are elements. N log 2n, okay, that's, well, it's order n times the logarithm of n, so it's getting a little bit slower. Log n squared, okay, or quadratic, that's a complexity of a polynomial sort of feature. You could go up from there to cubic, okay? You could go up from there, like you could say n factorial. That would be a big one there, right? So obviously complexity gets bigger and bigger or faster and faster. We don't need to put a million mathematical equations in here. For you to kind of see, like a movie system, it's on a scale, right? From order 1 being the fastest, yeah, to order n cubed being the slowest. It's pretty intuitive at that point. Okay, so the linear search is order n. The binary search, log 2n. The bubble sort, n squared. The selection sort, also n squared. And the quick sort, which is one we didn't have time to look at in class, quick sort algorithm by definition is faster, is log 2n. Now, you might be thinking, well, that's not as fast as binary search. Well, that's true, but binary search is a search algorithm, and quicksort is a sorting algorithm, okay? And the general rule is if it's a single loop, then it's order n. If it's 2 loops nested, it's n squared. And if there's 3 loops nested, it's going to be n cubed. That's a simple way to look at it. And then, of course, the algorithms get more complex, like binary search, when the loop isn't going to necessarily complete at the end of the list, like it's more of a while loop than a for loop. Okay, now that's the formal part of what I wanted to present to you guys, the formal sort of presentation part there. Now what I want to do is go into something a little less formal, okay, and discuss some of these other things on here. So yeah, we've talked about big O notation, okay? By the way, big omega and big theta, there's also something called little O notation. That's just sort of semantics, just different terms for the same thing, right? Like, you know, anyways. What I wanted to now get into, greedy algorithms, linear recurrences, and divide and conquer algorithms and dynamic programming. All right. The one I don't want to do is linear recurrences. I'll put a link to that one. Linear recurrences is very mathematical in nature, okay? What I'm going to do is start with the divide and conquer. This is a fun one. So I'm just going to discuss this with a little drawing. Okay. So, and Chelsea, please don't criticize my drawing skills at this point. I'm drawing in paint with a mouse right now. Santa, this is Santa. Santa Claus has gotten ready for Christmas time, and he's put together all his presents for Christmas night. Okay? Boxes and boxes of Christmas presents are ready to go out on Christmas night. Okay? And they're ready to go. And what he has is he has 1,000, or let's say 10,000 Christmas presents ready to go out, all boxed up like this, all tied in their bows and ready to go. And all of a sudden, he realizes that he's left his dirty socks in one of the present boxes. He accidentally left his socks sitting inside one of the presents. Inside the 10,000 presents, sitting inside one of them is his dirty socks. And he doesn't want to send this out to the kids because that would be disgusting. So he says to his Christmas elves, I need you to go and open up all 10,000 presents to figure out which one has my socks in there. But the elves are union workers. And they're like, nope, we're not going to do this. Our shift is up and we're not going to work overtime today. It would take too long for me to go through all 10,000 presents. But then one of the really smart elves came up with an idea. They said, you know what? We have a big scale in the back room of here at the Santa's workshop. And why don't we, on one side of the scale, put one present, and on the other side of the scale, put another present. And if the socks are in one of those, it's gonna be heavier. So the one with the socks inside would be on the side that's heavier, and we'd be able to figure it out right away. So all we have to do is keep putting presents on scales, one present versus another, and we'll figure out, we won't have to open the presents, we'll figure out which one has the socks inside. That way we don't have to open every single box and then rewrap every single box. And the elf union says, well, that still would take too much time. So then the elf came up with another genius idea. They said, what if we put not one present, but 5,000 presents on one side, and then 5,000 presents on the other side of this big scale. Whichever side of the scale gets weighed down, we happen to know that the socks would be in one of those. And then what if we cut it in half again? What if we put half of the ones from the heavy side onto another scale? And if we just repeat this over and over again, we'll get down to 2 presents. And then when we figure out which one's the heavier one, then we'll know which one has the socks in there. This is a silly way to explain the idea of divide and conquer programming. It's very much like the binary search. Actually, the binary search is an example of divide and conquer programming. Okay, so although it's listed here as a technique, which it is, and it's analyzed in its technique, in terms of like what it actually is, it's not necessarily that complex of a thing to think about. Okay, second thing I want to talk to you guys about is the idea of the greedy algorithm. The greedy algorithm is not necessarily an efficient algorithm. A greedy is a way to describe just a way that you just want to get it done fast and efficiently. Okay, so when it says here the idea of greedy algorithms, okay, it would be a discussion around like when would this be a good idea to do this. So this expands maybe beyond the idea of time complexity. Like when would it be the best idea to just use an algorithm that just works, period. So to do this, I'm going to use an example of a tree. So we have a 7 at the root. We'd have a 3 here. It's not in order, this tree. We'd have a 99 here. And I cannot draw it all today. We'd have an 8 right here. We'd have a 12. We'd have a 5. And we'd have a 6. Okay, so let's say we had to write an algorithm that said, okay, I'm going to start at the root and travel down from the root of this tree. If you travel to any leaf node, okay, and you summed up what the values are, you added them, like say 7 plus 12 plus 5, or 7 plus 3 plus 8, what would be an algorithm that would find the largest sum or the biggest sum? Which is the biggest, okay? So what a greedy algorithm just does is it just decides I'm always going to go to the bigger number. So it would start at 7, and then it would look at 3 and 12 is the bigger number, and it would pick that. And then it would go between 5 and 6, and it would pick the greedy or the biggest number, 6, and it would add those up and get 25. And the greedy algorithm would say, the answer is 25. That's actually not the correct answer, though, because if we look at this, if I went 7, 3, 99, 7 plus 3 plus 99 is 109. So greedy algorithms aren't necessarily the correct algorithms, but they can be the easier algorithm, right? And from a programmer perspective, sometimes that's going to work for you, right? Rather than write a big fancy piece of code that has to search through every single instance, my greedy algorithm would just say, always just go to the biggest number. Just go to the biggest, go to the biggest, go to the biggest. So that's what they mean by the greedy algorithm. All right, my final thing to look at here for algorithm analysis today is the idea of dynamic programming. Okay, so I want to go back and just review. So I'm actually going to put a link. This is actually a presentation I have. It's actually got the quicksort algorithm at the front of it. And then it's got some discussion on these algorithm efficiencies that we looked at. You obviously saw me talk a little bit about big O notation, about the divide and conquer idea, and the greedy algorithm. And we're going to end with dynamic programming. Okay. And this again covers a lot of what algorithm analysis, let's just relook at these things, right? So algorithm analysis, what is a worst case? What is big O notation? We could look at different sorting algorithms. Well, we essentially did that, right? So this would be the final piece of that 20S course that essentially you would have an introduction to. Even at this second level computer science course, right? You can see here that they really want you to take a little bit of mathematics and statistics before you take this course. But you can see here, analysis of algorithms, logarithms, summations, binomial theorems. Some of this you might have covered in IB math, right, as well. Big O notation. Again, I'm not sure why they put the H there. That is weird. The idea of the greedy algorithms. Recurrences, linear recurrences. This is, again, very math heavy, homogeneous, non-homogeneous, changing variables, master theorems. This is very math oriented. Divide and conquer, we talked about that. And finally, we're going to talk about dynamic programming. Okay. For dynamic programming, I'm actually going to do an actual little piece of code here for you guys. This little piece of code I will also put up into GitHub, and in the comments in this code, I will actually put some links as well. I'll also put them on the website. So what I'm going to do is I'm going to go back all the way to main, and I'm just going to run the tester code. And from the tester code, I'm just going to run the computer science 42 SIB code. And from the computer science 42 SIB code, I'm going to take all this out. And instead, I'm going to make a new post-secondary. And this will be something I can add to in the future classes as well. So for example, if we look at other stuff that would apply in Java, we'll go to this. But anyways, I'm going to create a class, post-secondary test. This is just another testing class. I'll comment it up later, get rid of a little bit of this code. Okay, so what I want to do and again, I promise I'll make it look pretty before I put it up in GitHub, is I'm going to use an algorithm what we've already seen, the Fibonacci sequence, which is done recursionally. So the answer to the Fibonacci of 5. Okay. So what would be the Fibonacci of 5? Create a method. What is the Fibonacci of this number? Okay. We already know kind of how this works. If n equals 1 or n equals 2, then the answer is 1. So you might remember, just a brief comment here, the Fibonacci sequence goes 1, 1, 2, and then you might remember it starts with 2 ones, and then this number is the other 2 numbers added together. So 1 plus 1 equals 2. The next number right here would be the previous 2 numbers added together. So 1 plus 2 is 3. 2 plus 3 is 5. 5 plus 3 is 8, etc. That's how the Fibonacci sequence works. Okay? So if I said, what's the Fibonacci of, this is 1, this is the second Fibonacci number, this is the third Fibonacci number, this is the fourth. What's the Fibonacci of 4? It would be 3, right? Okay, because 1 plus 1 is 2, 2 plus 1 is 3, 3 plus 2 is 5. What's the Fibonacci of 5? It's 5. What's the Fibonacci of 6? It's 8. So if it's a 1 or a 2, then the answer is 1. Otherwise, what I would have is the Fibonacci of n minus 1 plus n, the Fibonacci of n minus 2. This is a recursive method, okay? So let's see if this works. The Fibonacci of is my answer. Okay. Let's see what happens. No, nothing new here. This is just recursion. You've seen this before. I don't think we did the Fibonacci number, but there it is. The Fibonacci of 5 is 5. That makes sense. Let's take it up to 6. So it should give me 8. Come on. Yep, so it seems to be working. And there's nothing wrong with this algorithm. But what I'm going to show you now is another way to do this. Okay? My answer is going to come from my second version of Fibonacci. Okay? And I'll output it again. And I'm going to write a second version of this Fibonacci method. Okay? With this version, I'm going to use the idea of dynamic programming, which is if you notice that a lot of your code tends to be repeating, there might be a slightly more efficient way to do it. So here's what I mean by that. When I did the Fibonacci of 5, it had to do the Fibonacci of 4 and the Fibonacci of 3. When it does the Fibonacci of 3, it does the Fibonacci of 2 and the Fibonacci of 1. Now, these would be essentially leaf nodes because, as we saw up there, the Fibonacci of 2 is 1, the Fibonacci of 1 is 1. Okay? But then when it does the Fibonacci of 4, it's the Fibonacci of 3 and the Fibonacci of 2. That's a leaf node right there. But 3 would be the Fibonacci of 2, and it would also need to know the Fibonacci of 1. And what I would see is this equation, figuring out what the Fibonacci of 3 is done twice in this idea. To get what the Fibonacci of 5 is, Fibonacci of 3 is done twice. In addition, the Fibonacci of 2, although it's a base case, is done 3 times. Okay, so that's not efficient. I keep repeating the same code, in this case twice or 3 times. So in dynamic programming, to fix that, what I'm going to do is I'm going to make a result variable. Okay, and the other thing I'm going to do is I'm going to, well, actually, no, what I'll do is I'll wrap this method in another method. I'm going to return the Fibonacci, this is a dynamic version, of n and an array, which I'm about to create in the line above this. I'm going to make an array. Okay. And actually, in order to fill it with null values, I'm going to make it an integer array. How big will it be? It'll be n plus 1 in size. Okay? All right, here we go. So now I have 2 parameters. The number I'm calculating the Fibonacci for, and an array itself. Now I've hidden that because back here I just asked for n, and then I call a hidden little private or wrapped method the dynamic method here. Okay, so here's what I'm going to do. I'm going to make a result variable equal to 0. The end of this method, that result is what I'll be returning. So dynamic algorithms tend to use the power of memory to help with the efficiency here. If a spot n is not a null, then I return n. So now I'm using the array to store results. Okay, if you remember the tree I drew here, I drew that tree here. I'm not going to put the numbers in and all that, but I had a tree that looked something like this a few minutes ago on the projector here. And in that, we realized that this and say this one were happening at the same time. So the first time I do this, why don't I just store that in my array so that if it ever comes up again, I don't need to recalculate it. I'll just go into my array to figure out what the answer is. So that's kind of what's going on there. Okay, else. Okay, so now it's essentially, well, I actually don't need an else here. It would be essentially the same code as up here. If n equals 1, but instead of returning 1, okay, what I'm going to do is I'm going to assign the result to be that. The result equals 1. Okay. Else. Now what I'll do here is, again, I will do this idea of the recursive call, but I'll say the result recursive call and a spot n will equal the result. So it's a slightly different algorithm, as you can see here, but it's using some memory, both the array and a temporary result variable, to try to make the algorithm a little more efficient. So first off, let's see if we get the same answer out of both algorithms, because that would be important, right? It'd be important for it to do that both times, and it does. Okay, now what I'm going to do is I'm going to put the second one inside of a loop using n as the looping value. Okay, so put this. Answer being a temporary variable inside of this. And then same with up here. N variable. Put this. Okay. And stopping point of this. Let's start it off at 20. Okay, so I'm now going to stop these two loops at 20. So the first one uses Fibonacci 1 algorithm. And this uses Fibonacci 2 algorithm, which is our dynamic algorithm. Okay, let's see what happens. Well, we are already too big here at 20. Let's go down to 10. Fibonacci's get big fast. All right. Let's increase the size of this. And okay, let's see. That pushes things up a little bit. Nope. What am I doing here? Okay, let's just take it down to 8. Or how about 6? We knew 6 worked before. Oh, I'm missing something. Okay, I'm going to fix up that code. I can see we're almost out of time. I'm not sure what I did wrong here. Just want to see where that crash is happening here. It's crashing on the first one. You know what? It might just be, again, these ideas of integers. Let's just make everything longs. Universe happy. Okay, guys, I'm gonna clean that up, and I'll have that all commented up for you guys. I don't want to waste our time here on this. I just want to put the last 2 minutes, 2-3 minutes of this available for you guys for any questions you guys might have, if you have any. That was a lot. That was like a regular class for us in some ways. So I actually have a massive headache today. So listen, guys, no matter what, please, as I mentioned before, take a minute to look on the alumni page to watch these 2 videos. They really, I think, could be quite inspiring for you guys moving forward in a tough time right now. Okay? Do you guys have any questions? Are any of you even left in here? Let me just check. Oh, yes. Darwin and Shanae are here. Okay, guys, I'm going to end then. Thanks, guys. Next week, I'll update the website to give you an idea what I'm planning for next week. And this video has been recorded, so I will also have it up on the website. And I'll update GitHub and all the rest. Okay, guys, stay safe, and I'll see you soon.
Thanks.
Bye.
Bye.